Good morning, everyone. Welcome to another lecture under Advanced Structural Design. For today, we will be advancing to our new topic, which is shored and unshored construction. Before we proceed to our discussion for today, I would like to talk about first our activity for today. So after our discussion, you will be having your first seat work, which will be placed under the quiz tab on your Canvas accounts. So I would like everyone to listen very carefully during our lecture. I would like to remind as well everyone about our remaining lectures for midterms. Including today and the next week Monday, we only have 2 days left for your lectures. Take note that next week Thursday now is the schedule of your midterm exams. So, do expect that by next week Monday, I might be giving your quiz right after our last lecture for Advanced Structural Design. Alright, so do not forget those reminders. Now, let us proceed to our discussion proper. Alright, so before we proceed now to our discussion under shored and unshored construction, let us recall first what we have discussed last meeting. So last meeting, I have introduced to you now composite beams, wherein we were able to discuss and solve one sample problem. Alright, regarding this problem, I would like all of you now to go back to your notes regarding composite beams. So regarding that problem, there might have been a few or a slight mistake which we have missed during our computation. Alright, so we have this one. So kindly go back to our discussion last meeting to your notes if you have one. Alright, so kindly take a good look at the topmost part computation now of our beam. Now, I would like to thank some of you or the student now who was able to ask about this question. Now, I might have missed to uh, include this one during our discussion. So take a look at the computation now for the topmost part. So if you are going to input now the value for FST, we have 500. You have there 500 times 10 raised to 6, multiply that to 200.18, divided by the transform moment of inertia, which is 117.32 times 10 raised to 6. The value there isn't automatically 7.74 MPa, right? The value that we will have is 61. This will give us 61.89 megapascal. Now, this might have caused some confusion to some of you. All right, so I forgot to include this on our computation last meeting. That for the computation for the topmost part, for composite beams, we are going to divide the value or this value now by the modular ratio. So this will be divided by the modular ratio, which is equal to 8. Now 61.89 divided by 8 will give us a final answer which is equal to 7.74 megapascal. Alright, so that is one of the corrections now for our from our previous example for composite beam. Alright, so kindly check that one on your notes. Now I do know that you were unable to apply this one on the plate that I have given you, so I will be giving some consideration now. So I will be giving some consideration regarding this matter. All right, and then another one, I do not know why none of you asked me about this matter. Now I do know that you already finished RC1, right? wherein in RC1 you have already discussed about allowable stress. Alright, so this is the reason why why I did not include this part now on your plate number 2. So take a good look at this one. Now when I say allowable stress, what does it mean? Take note, when we say allowable stress, that is the maximum stress, be it tensile, compressive, or bending, which is allowed on a structural material. So our allowable stresses are, for your concrete, that is, or FC, that is 9 MPa. And then allowable stress for FS or steel, we have 150 megapascal, right? So those are the allowable stresses, which means we cannot, here, we cannot exceed these values, all right? So if we are going to compare now the value of our topmost part with our FC here, it is less than now 9 MPa. So instead of fail, I'm sorry, but I'm sorry again for this one. So instead of fail, this should have been adequate. So, or it passes now the criteria. So kindly correct again. I'm very sorry again for this one. And then same goes, if we are going to compare now the bottom part now of our composite beam, the stress at the bottom part of our composite beam with uh, the allowable stress for steel, which is 150 MPa, it is less than now the allowable stress for MPa, which is the maximum stress that is allowed for that steel material. Instead of fail, it is now adequate. Adequate. Which means that the composite beam now is able to carry the weight that is placed onto it. Alright, once again, I would like to apologize now for the corrections that I have made during our discussion last meeting. And I would like also to commend those students who were able to ask me regarding about this matter. So kindly correct your notes, and then proper adjustment now will be made according to your plate. Alright, so kindly take note of these corrections. Alright, so we are going to apply these corrections now in solving for your plate number 2 later on our discussion proper. Alright, so let us now proceed to our discussion. So for this discussion, I have listed here 2 topic learning outcomes. So by the end of this lecture, the student should be able to properly compute for the stresses of a composite beam of concrete slab and then structural steel, and then differentiate properly shored and unshored construction. So the second topic learning outcome would be our discussion for today. All right. So before we proceed to our proper or new topic, let us recall first what are composite beams. So as I have said last meeting, a composite beam, it is a structural member which is composed of 2 or more dissimilar materials which are joined together to act as a single unit, which the resulting system is stronger than the sum of its parts. Take note of our example last meeting, that is a combination now of a steel I-beam and then a concrete slab, right? Wherein we were able to transform the concrete slab into steel for us to be able to determine the stresses. Alright, so we also have here your modular ratio, wherein the modular ratio is utilized now for us to be able to transform your concrete slab into a steel. Wherein take note, what if we are tasked to determine the real value of our modular ratio? That is because from our previous example, including your plate, the modular ratio is readily given. So how are we going to compute the real value of your modular ratio? So let us denote here. The modular ratio is denoted as N. So how are we going to do that? That is just computed utilizing the elastic of modulus of elasticity now of the two members or the two structural members composing your composite beam. So you are going to divide the modulus of elasticity of the higher material divided by the modulus of elasticity of the other material. So in our case, from our previous example, that will be the modulus of elasticity of steel, which is ES. Divide this one now by the modulus of elasticity of concrete. All right, so the modulus of elasticity for steel is equal to, that is 200 times 10 raised to 3 megapascal. So that is MPa. But for the modulus of elasticity of concrete, we can compute this one as from your reinforced concrete one. If you are going to recall your discussion on the reinforced concrete one, for us to be able to compute the modulus of elasticity of concrete, what do we utilize? That is, we have your 4730 square root now of FC prime. Wherein take note, FC prime now is given on the problem. Alright, so I repeat, for your modular ratio, if you are tasked to determine the real value now of your modular ratio, you can utilize the modulus of elasticity of the two members composing your structural or composing your composite beam. Alright, so that is for composite beams. Now, we have here your plate number 2. So it says here, the data given are, we have your FC prime, which is equal to 20 megapascal, your Fy, which is equal to 248 megapascal, and a modular ratio, which is equal to 8. So you are tasked to determine the transform moment of inertia, and then at the same time, determine the stress at the bottom of the beam, interface, and then the topmost part of the beam. So I did not include here now comparison of the stresses. That is because uh, of the correction that we have made, that I have corrected earlier. So, however, I was really hoping that a lot of you would come and ask regarding about the comparison of these stresses. So nonetheless, now at least I was able to correct it with you. So we are going to include that one now in our computation. So let us try to say, for example, before we proceed to solve for letter A, B, and then the comparison of the stresses, say for example, what if we are tasked to determine the real value now of our modular ratio? So let us try solving that one. So let us denote it here. The real value now of our modular ratio, we have here real value of n. So for the real value of n, that will be n is equal to the modulus of elasticity of steel, which is 200 times 10 raised to 3 megapascal, right? Divide this one by, we have here 4730 square root of Fc prime, which is 20 megapascal. So n now would be, input that on your calculators, I will have here 200 times 10 raised to 3 divided by 4730 square root of 20, which is now 9.45. Right, sana yun? Which is now 9.45. So observe now or compare what we have, the real value of n, and then the given on the problem. So regardless of the real value for n, we are still going to utilize here the modular ratio, which is equal to 8 in our computation. All right, so let us proceed now to the transformed moment of inertia. All right, observe now that for our concrete slab here, we have here a length which is equal to 1.2 meters. So our first task here is to transform our concrete slab into a steel. We have your diagram here. And how are we going to do that? We are going to divide the width now of the concrete slab by the modular ratio. So we will have here transformation now. So let us denote that as the transformation TR is equal to 1.20 meters. Divide this one by 8, or TR is equal to 1,200 mm. Divide that one by 8. TR now is equal to, you have here 1,200 divided by 8, that is 150 mm. So we have here 150 mm now as the transformed length of our steel section here on our second diagram. So that is, or this is 150 mm with a thickness of steel 100 mm. All right. So next step, we are going to determine now the location of our neutral axis. All right. So say for example, let us try to determine first the area of each section. So if I were to do that, areas here. So let us start off from the very at the top up until to the bottom. So I will have here 150, multiply this one by 100, and then we will have here 18 by 225 mm, and then we will have here 16, multiply that by, that is 375 minus 18 times 2, I will have here 339, 339, and then another 18 multiplied by 225. So 150 times 100, that is equal to 15,000 mm. 15,000 mm, and then I have here 18 times 225, 4,050, and then 16 times 339, 5424, 5424, and then this is also 4,050. Total area which is equal to, that is now 15,000 plus 4,050, 5,424, and then 4,050, which is 28,000. I have here 28,524 millimeter squared. All right, so we can now determine the location of our neutral axis. Say for example, let us try to determine it from the top of our composite beam. All right, so if I were to try to determine the neutral axis, we have to utilize your Varignon's theorem in computation for our neutral axis. So we have your Varignon's theorem. So I will have here area total, which is equal to 28,524, multiply this by the distance of your neutral axis to the top now of our composite beam, equate that to each of this area. All right, so say for example I have here 15,000, and then the distance now of our steel section, the centroid to the top, so that is multiply this one by 50 plus what else, that is equal to 4,050. The distance now, the centroid to the top, that is equal to 100 plus 18 divided by 2. I have here 109. Sorry. Then what else? Plus 5,424. Multiply this one by, that is now equal to 375 divided by 2. Add 100, that is 287.5. I have here 287.5, and then the last one plus 40, 50. Multiply now this by 375 minus 9 will give me 366 plus 100, 466. Take note, the distances that I am placing here are the distance of each of the section from their centroid to the top now of the composite beam. That is 466. Why to the top of the composite beam? That is because we are trying to determine the location of the neutral axis from the top of our composite beam. Alright, so we have this notation. Divide both sides by the total area. So this is now 28524, which will cancel out. And then this part by 28,524. Y top now is equal to, I will have here 15,000, multiply that by 50, plus 4050 times 109 plus 5424 times 287.5, and then the last one 4050 times 466 divided by 28,524. I have here 162.61 mm, right? So that is 162.61 mm. So from the top, that is now, this is 118, and then approximately it is now located, or our neutral axis, basing it from what we have computed, will be located at this part now. So I have here now our neutral axis, wherein from the top, the distance now is equal to, here, y top is equal to 162.61 mm. Therefore, y bottom now, yb is equal to, that is now 475 minus 162.61 is 312.39. So we have here 312.39. So we already know the location of our neutral axis. We can now easily solve for the transformed moment of inertia. So say for example, let us place it here. So for your transform moment of inertia, let us denote that one as ITR. That is now 1 all over 12 BH cube plus AD squared starting off from the first section. Take note, we are dealing here with rectangular sections. Alright, so I will have here ITR now is equal to 1 all over 12, that is 150 times 100 cube plus 15,000. Its distance from the centroid is 162.61 minus 50, that is 112.61. All right, so I will have here the base now, which is equal to 150 times the height of 100 cube plus an area which is 15,000, and then the distance now, its distance from its centroid to the neutral axis is 112.61. So I will have here 112.61 squared. Then proceed to the next section. 1 all over 12 base is equal to 225. Multiply this one by its height, which is 18 cube, plus its area, which is equal to 4,050, and then its distance now, its distance from the neutral axis. So that will be 162.61 minus 100 minus 9. So we will have here 53.61. So I will have here 53.61 squared. Then the next one, that is 1 all over 12, multiply this by the base, which is equal to 16, and then its height, which is, that is now 375 minus 18 times 2 again, that is 339. 339 cube plus the area, which is equal to 5,424. 5,424, and then its distance from the from the neutral axis, that is now equal to 124.89. So we have here 5424, multiply this by 124.89 squared. And then the last section, that is 1 all over 12, multiply this by, I have here 225 as its base and a height of 18 cube, plus its area, which is equal to 4,050, and then its distance from its centroid to the neutral axis, that is 312.39 minus 18 all over 2, which will give me 303.39 squared. All right, now input all of this on your calculator, and then it will give us a total value now for your transform moment of inertia, which is now equal to, we have here 723.903 times 10 raised to 6. This is now millimeter raised to 4 as our final value now for your transformed moment of inertia. All right, so that is for our computation for the transformed moment of inertia. Let us now proceed to the next question. So we have here your conditions provided that if M now is equal to 100 kilonewton per meter, we are to determine the bottom stress at the bottom of the beam, at the interface now, and then at the topmost part of our composite beam. So let us start off our computation with letter A. So for letter A, at the bottom part now of our composite beam, I have here FSI now is equal to, that is M, which is the moment, multiply this by our distance now from the bottom of the composite beam, that is Y bottom, all over the transformed moment of inertia, which is IT R. So our M now is equal to 100 times 10 raised to 6. Multiply this one by what is now our distance that we have computed earlier, that is 312.39. So we have here 312.39 mm all over our transform moment of inertia, which is 723.903 times 10 raised to 6 millimeter raised to 4. So what will happen here now? We will have here, input that on your calculators. I will have there 100 times 10 raised to 6 multiplied by 312.39 all over 723.903 times 10 raised to 6. We will have here 43.15 megapascal. Alright, so let us now proceed to the next item, which is the stress at the interface now of our composite beam. So for the interface, there are two possible answers. So let us start off first with the steel interface. So we have here the steel interface. Let us denote the steel interface as Fi sub S, wherein we can compute this one as the moment, which is 100 kilonewton per meter, multiply this one by Ci, wherein what is Ci again? That is its distance, or the distance of the interface of the transformed steel section, and then the I steel section, or our I beam, to the neutral axis, divided by the transformed moment of inertia. So we will have here 100 times 10 raised to 6, multiply this one by going back to our diagram, that is now 162.61 minus 100 will give me 62.61. So I will have here 62.61 all over transform moment of inertia 723.903 times 10 raised to 6. Now for the steel interface, that will give us a value which is now equal to 8.65 megapascal. So I have here 8.65 megapascal. Now, if we are going to compute now for the concrete interface, for the concrete interface, let us denote this one as Fi sub C. That is just the steel interface, or Fi sub S, divided by the modular ratio. So that is 8.65 divided by 8, which will give me 1.0. I have here 1.08 megapascal for the concrete interface. And then letter C, for the topmost part now of our diagram, So I will have here Fs sub t is equal to m multiply this by y top all over transformed moment of inertia. So that is 100 times 10 raised to 6. Multiply this one by 162.61. So I have here 162.61 divided by, that is now 723.903. Multiply that by 10 raised to 6. We will have here, that is now 162.61, 22.46. So we will have here 22.46 megapascal. But take note, this one is not our final answer, since according to our correction earlier, what will be the final value now of FST, or the stress now at the topmost part of our composite beam? I will have here Fs sub t now is equal to 22.46 divided by the modular ratio, which is 8. I will have here 46 divided by 8, 2.81 megapascal. So I have here 2.81 MPa as our final answer for the topmost stress now of our composite beam. So from here, we can now determine the allowable stresses and then compare them with Fs sub I, or that is the bottom stress of the composite beam, and then Fs sub T, which is the topmost stress of the composite beam provided. Alright, so let us now proceed to the allowable stresses for the said composite beam. Alright, so for the allowable stresses, we have here your conditions. We have Fc, or the allowable stress for concrete, which is 0.45 Fc prime, and then Fs, the allowable stress for steel, that is 0.60 Fy. So according to the problem, we have a value for Fc prime, which is 20 megapascal, and then Fy, which is 248 megapascal. Thus giving us a value for Fc now, which is equal to 0.45, multiply this by 20, and then Fs, which is 0.60, multiply this by 248 megapascal. So our allowable stresses now is equal to 0.45 times 20. I have here 9 megapascal, and then 0.60 times 248, that is 148.80 megapascal. So observe now, these are our allowable stresses. So compare these allowable stresses with the stresses that we have obtained for our composite beam. So for the first one, if we are going to compare the bottom stress of our composite beam, which is 43.15, so that is the bottom stress, that is Fsi. So I will have here compare now. For the Fs sub I, which is the bottom stress of the beam, 43.15 megapascal, this is now less than the allowable stress, Fs allowable, for the steel section, which is equal to 148.80 megapascal. Now, since, as I have said earlier, the allowable stress is the maximum stress that is allowed on a structural member. Alright, so since the stress of our composite beam did not exceed the allowable stress, We can therefore conclude now that the stress now at the bottom part of the composite beam is adequate, or it will not fail. And then the last one for FST, that is now equal to 2.81 megapascal. So we have here 2.81 megapascal, which is less than the allowable stress for concrete, which is equal to 9 megapascal. Now, it did not exceed the maximum allowable stress, so this one is also adequate, which means that the given composite beam now is capable of carrying the loads which are given unto it. All right, so that is now the solution for your plate number 2. As I have said, proper consideration, since there were corrections during our last lecture, will be given now when correcting your plate number 102. So do take note of the corrections that we have discussed earlier, and then I do hope that you are now familiar in solving composite beams. All right, so we will now proceed or discuss shored and unshored construction. Okay, so let us now proceed with shored and unshored construction. Now, what do we mean when we say shoring? So it says here, shoring is a form of prop or support which is usually temporary and that it is used during the repair or construction of buildings and excavations. So temporary support may be required, for example, to relieve the load on a masonry wall while it is repaired or reinforced. Say for example, take a good look at this diagram. So if you are going to take a good look at this diagram, we have here your walls, reinforced walls, which are um, undergoes curing. So we have here your struts, braces, posts, which are used now to support these reinforced walls. So what do you call this braces, posts, struts? That these are now your horizontal or flying shores, which will then be removed if curing now of this reinforced wall is complete. All right. But in our case, since we are talking about composite beams, it says here, shores are temporary members which are used to support curing member, usually, which are usually composite beams. As I have said earlier, the shores, which are this one, this part of the diagram here, take a good look at the arrow, horizontal flying shores, we have this one, are used to support curing members. All right. So let us define what are shored construction and then what are unshored construction. Now, when we say shored construction, it says here, in this scenario, the steel shape is designed to support only its own weight. All right. And then under unshored construction, there are two types that we are going to consider. We have your curing stage and then the composite stage. For the curing stage, it says here, the steel shape alone must have sufficient strength to resist all load. It says here, um, example of the loads that it will resist, we have your self-weight, weight of concrete, and then construction load, which are then applied before concrete attains now, take a note, this one, 75% of its strength. That is for the curing stage. How about the composite stage? The composite stage now will, it says here, the composite beam will support all loads subsequently applied. All right. So for you to better understand short construction and unshort construction, I have prepared here an example which we will try to solve again and see the difference now between short and unshort construction. All right. So I have here sample problem wherein it is asking us to determine now the stresses in the extreme fibers if the construction is letter A, shored, and then letter B, unshored. So take a good look at the diagram. So this part now is similar to your plate number 2, right? That is because the first part now of our computation is for us to transform the concrete slab provided in the diagram into a steel section. Then after transforming that, utilizing again your modular ratio, which is equal to 8, which is given, transforming this one to a steel section, we are going to determine again its transformed moment of inertia. Luckily, we did that already a while ago. So we can utilize this one now for our computation for shored construction and unshored construction. However, take a good look at this one. Additional information are given in the problem. We have here your loads. The loads here now will be utilized in computing for the stresses that are present during shored construction and then unshored construction. Then at the same time, we will be comparing now the stresses obtained from these two to the allowable stresses obtained now from Fc prime and then Fy here, right? The process of obtaining now the allowable stresses is the same as what we have discussed already under composite beams. All right, so let us start off in determining now the stresses in the extreme fibers in shored construction. All right, so I repeat, the very first step is for us to transform our diagram now into, or transform our concrete slab here into a steel section. Luckily, we did that a while ago. So we already have here, from 1.2 meter, we have here 150 mm by 100 mm steel section. So from there, we were able to determine its neutral axis, and then from there, we were able to obtain now its transformed moment of inertia. We will be utilizing this one now in determining again the that would be the stresses at the topmost part of our diagram and then at the bottom part now of our composite beam. So say for example, let us start off with shored construction. So observe now that during our examples under the composite beam, the value for M is readily given. In our case, we will have to solve for the value for M. That is the use now of the loads which are given on the problem. All right, so let us determine the value for M under shored construction. Now, for us to be able to determine the value for M, we are to utilize the equation M now is equal to WL squared all over 8, wherein we need to determine first the weight total the composite beam could carry under shored construction. So for shored construction, if we are going to go back to the definition, it says there, it is designed to support only its own weight. Regardless of what is being said, instead of utilizing only the weight of steel, we are going to include now both dead and live load now on our computation. Take note, WL here is the live load. WCL here is your construction load. We have here unit weight of your concrete, weight of steel, and then weight additional here will be considered as part of your live load. And then I have here length, which is equal to 6 meters. This is now the span of your concrete slab. All right. So from here, let us start our computation for W under shored construction. So for weight total, we are going to include first your live load, which is equal to 6, and then add now the construction load, which is equal to 2 kilonewton meter squared. Then what else? We are also going to include now the additional load, which is 0.75 kilonewton meter squared. So I will multiply this one by the length now of our concrete, which is equal to 1.2 meters. Take note, the span which is given on the problem will be utilized here in computing for the value for M. What else? So the value here now is in kilonewton meter. I am going to add now the weight of the steel, which is equal to 5 kilonewton per meter. Then what else? I also need the weight of the concrete itself. So that is now plus the unit weight of concrete is given, which is 23.56. Multiply it by the dimension of the concrete slab, that is now 1.2 by 100 mm, or that is 0.1 meters. So weight total now will therefore be, input that on your calculator, I will have there 18.33 kilonewton meter. So kindly check. I will have here 6 plus 2 plus 0.75 times 1.2 plus 5 plus 23.56 times 1.2 times 0.1, 18.33 kilonewton meter. So substitute that one on our equation, which is WL squared all over 8. We will have a value for M, which is equal to, M now is equal to 18.33. Multiply this by the span, which is equal to 6 meters. Raise this to 2 divided by 8. So the value for M now, which we are to utilize in computing now for the stresses in the extreme fibers, would be 18.33 times 6 squared all over 8. That is now equal to 82.485 kilonewton meter. So I have here 82.485 kilonewton meter. All right, so now that we already know that, what are we going to do? So we are going to determine now the stresses at the extreme fibers. So stresses now. So say for example, let us start at the topmost part now of our composite beam. So if we are to determine the topmost part of our composite, the stress at the topmost part of the composite beam, let us denote that one as FC at the top, FCT. Wherein what will happen here, that is now M, multiply this by YT all over transformed moment of inertia. So that is now FCT is equal to, M here is 82.485. Take note, this is in kilonewton meter. So if we want our answer to be in megapascal, this is now multiplied by 10 raised to 6. 82 yan. And then what is the value for Y top? The value for Y top now here is 162.61 mm. So I have here 162.61 mm divided by the transformed moment of inertia, which is equal to 723 0.903 times 10 raised to 6 millimeter raised to 4, Fc transformed now is equal to, I will have here 82 point, this is 82.485 times 10 raised to 6, multiply this by 162.61 all over 723.903 times 10 raised to 6. I will have here 18.53 megapascal. But take note again of what we have discussed earlier. For the stress at the topmost part of a composite beam, what are we going to do? We are going to divide the value now by the modular ratio. So if I were to divide this one now, take note this is the stress transformed at the topmost part of our composite beam. So if I were to divide this one by 8, from stress transform, I will now have here the stress for concrete, which is equal to 18.53 divided by 8, that is now 2.32 megapascal. So we have here now the stress for concrete, which is 2.32 megapascal. Take note, this is at the topmost part. So how about at the bottom part now of the composite beam? So for the bottom part of the composite beam, we will be able to determine the stress for steel. So let us denote this one as F sub S. So what will happen? That is the same M multiplied by YB all over I TR, or the transform moment of inertia. Fs now is equal to the moment, which is 82.485 times 10 raised to 6. Multiply this by Y bottom there now is 312.39. So I have here 312.39 divided by the transformed moment of inertia, 723.903 times 10 raised to 6. Fs now, stress for concrete, is equal to, substitute that again on your calculators, we will have there a value which is equal to 35 point, I have here 35.60 megapascal. So we already have the stresses at the extreme fibers now of our composite beam. Take note, at the top, when you are determining the stress at the topmost part of a composite beam, you have to divide the value for My divided by the transform moment of inertia by the modular ratio for you to be able to determine now the stress for concrete. So we have this value. And then at the bottom, you will be able to determine now the stress for steel. All right, so check for allowable. If we are going to check now for allowable stresses, Fc allowable now, that is equal to 0.45 Fc prime, or that is 0.45, multiply this one by 20. Fc allowable now is equal to 0.45 times 20, 9 megapascal. Then same goes, Fs allowable is equal to 0.60 F y, wherein 0.60 multiplied by 248, I will have here 0.60 times 248, that is now 148 uh, 148, sorry, 148.80 megapascal. So check now, for the stress of concrete, the allowable stress for concrete is 9 megapascal. So it should not exceed 9 megapascal. So this is less than FC allowable. And then for Fs, the allowable stress for steel is 148.80, which is less than Fs allowable. So both stresses at extreme fibers are less than the allowable stresses, which means stresses now, the stresses at extreme fibers, are adequate under, we have here, shored construction. All right, shored construction. So which means that we can apply shored construction for problem number 1. So that's it for shored construction. Let us proceed to our computation for unshored construction. So for unshored construction, we will be considering two types of computation. As I have said earlier, for unshored construction, we have your curing stage and then the composite stage. So for our first computation, let us consider first the composite stage, or that is letter A, what we call as concrete wet. Now for concrete wet, instead of considering the whole composite beam, we are going to consider first the steel section only. Take note, it says here, consider the steel section only. Now, if we are going to consider the steel section only, what will happen? We need to determine again the moment of inertia. This time, we do not have a concrete slab attached at the topmost part now of our steel section. So what will happen to the stress? We will only determine stress for steel. No need to determine the stress for concrete since we are only considering the steel section. All right. Now, since the problem given is a symmetrical I section, we can easily determine the value for y top or y bottom. Since both are equal, what will happen? The value for y now is just the height, which is equal to 375 mm divided by 2. I will have there 187.5 mm, which we are going to utilize now in computing for our stress in steel. But before that, we also need to determine now the value for our moment of inertia. Now take note, if we are going to take a look at our diagram again, say for example this one, disregarding your concrete slab at the top, if I were to determine the transformed moment of inertia, the moment of inertia for the steel section only, take note that its neutral axis is located at the center. So what will happen, instead of considering again three sections, so that I can eliminate AD squared at the at the end of our equation for a moment of inertia, I will consider the whole rectangular figure. Then I will subtract these two rectangles for me to be able to obtain now, alright? Can you see these two rectangles for me to be able to obtain the moment of inertia for the steel section only. But if you would like, you can consider this three section and then compute as is as what we have discussed for the moment of inertia. Take note, considering the steel section only, since this is a symmetrical section, consider now symmetrical section, the y top and y bottom now are equal. What if you are given an unsymmetrical section, then you are trying to compute for the stress? So you are going to utilize the value for y, which is at the bottom. Take note, for concrete wet, when we are only trying to determine the stress for steel. So if you are given a unsymmetrical section, I repeat, you are going to utilize now y bottom. All right. Now let us go back to our problem here. We are trying to determine now our moment of inertia. So I here now is equal to, I will consider the whole section, so that is 1 all over 12, the base of which is equal to 225, and a height of, considering the whole section, 375 cube. Now the neutral axis now of this part is at the centroid, or the centroid now of this part is at the neutral axis, so no need to add AD squared. Instead, I will subtract here the moment of inertia naman for the two rectangles, as I have said earlier. So that is 1 all over 12, multiply that by what is its base. So take note, the base now would be 225 minus, I will have here 225 minus 16, and then divided by 2, that is, I'm sorry, 225 minus 16 divided by 2, that is now 104.5 mm. So I have here 104.5 mm and a height of, which is equal to 375 minus 18, and then minus 18, that is equal to 339 squared. Then multiply this again by 2. Now for those of you who cannot visualize, what I am trying to compute here now is, if this is my symmetrical I section, this part, alright, if this is our symmetrical I section, the neutral axis now is at the center. This is now our neutral axis. So observe now that if I were to consider this whole diagram here, considering this whole diagram, I will have this equation. Wherein I do not need to add AD squared since its centroid rests upon the neutral axis. And then same goes, since I considered the whole diagram and then our section is an I section, I will have to subtract this part. Now this part are equal, which is why I multiplied it by 2. And then no need to add AD squared because their centroid rests as well at the neutral axis. So the value of I now is equal to 1 all over 12, multiply that by 225 times 375, raise this to 3. Subtract this quantity by, that is now 1 all over 12 times 104.50 times 339, raise this to 3 times 2, which will now give me 310,247,217 millimeter raised to 4, or that is 310.25 times 10 raised to 6 millimeter raised to 4. Alright, so we already have your moment of inertia, the value for y. What's next? Determine the value for m. Same, for us to be able to compute for the value of m, we need the value for w, which is the weight total carried by the I section only. And then the weight, for us to be able to determine the weight, we are going to consider the dead loads only. And what are those dead loads? We have 5, which is the weight of the steel. What else? The weight of the concrete itself, that is 23.56, the unit weight of the concrete, times 1.2 times its thickness, which is 0.1. Then do we have anything else? That is, what else do we have? According to the problem, we have the weight of the construction load, which is 2 kPa. Weight of the construction load, which is equal to 2 kPa. But take note, that is 2 kPa, so what will I do? I will have to multiply it by the length now of the concrete, which is 1.2. Alright, so weight total now is equal to, considering the steel section only, that is now 5 plus 23.56 times 1.2 times 0.1 plus 2 times 1.2 here. I will now have 10.23 kilonewton meter. So I will have here 10.23 kilonewton meter. Substitute that here for the value for m. I repeat, for concrete wet, we are going to utilize here the dead loads given on the problem. All of the dead loads given on the problem. So m now is equal to 10.23 times 10 raised to 6. Multiply this by, I'm sorry, that is 10.23 only. This is 23.56. So 10.23, multiply this one by 6 squared divided by 8. The m now is equal to 46.02 kilonewton meter. So that is, let us check, 10.23 times 6 squared divided by 8, 46.0. 10.23 times 6 squared, that is supposed to be 0.4. So this is 46.04 kilo Newton meter. So for the stresses now, since we are considering the steel section only, we can only compute for F sub S, wherein for F sub S, that is now equal to my all over I. F sub S will therefore be, I will have here 46.04 times 10 raised to 6, multiply this by y, which is equal to 187.5, divide this by the value for I, which is equal to 310.25 times 10 raised to 6. Fs here now is equal to 46.04 times 10 raised to 6. Multiply this quantity by, that is now 187.5 all over 310.25 times 10 raised to 6. I will have here 27.82 megapascal. So we will not compare yet the value or this stress for steel to the allowable stress, since we still need to compute the other stage, which is the curing stage. All right, so that is 46.04 times 10 raised to 6, 187.5, and then 310.25 times 10 raised to 6, which will give me 27.82 megapascal. All right, let us proceed to the other one, wherein under the curing stage, let us denote that one as letter B. So that is now under concrete cure. For concrete cure, we will consider the whole diagram again. So we will be considering both steel, consider both steel and concrete section. So if we are going to consider both steel and concrete section, we are again going to utilize now the value for the transform moment of inertia, and then what we have computed earlier for the value for y top and then y bottom. And then for concrete cure, instead of utilizing dead load, under concrete wet, we utilize here your dead load. For concrete cure, we will be utilizing only your live loads. So what will happen? Weight total now will be equal to, what are your live loads given? We have live load, which is 6 kPa, kilonewton meter squared, plus your additional load, which is 0.75 kilonewton meter squared. Multiply this by the length of the concrete, which is equal to 1.2. Weight total now is equal to, I will have there 6 plus 0.75. Multiply this by 1.2. 8.10. I will have here 8.10. 8.10 kilonewton meter. So the value for M now is equal to 8.10 times 6 squared all over 8. M now in kilonewton meter, that is 8.10 times 6 squared all over 8, 36.45. I will have here 36.45 kilonewton meter. So we can now compute for the value for transformed stress for concrete and then stress for steel. So stresses again here. For our stresses, that is now equal to FCT at the bottom first. So what will happen? 36.45 times 10 raised to 6 At the bottom, that is 312, Y bottom, 312.59. Take note, we are considering steel and then concrete section again, the whole composite beam, divided by our transform moment of inertia, which is equal to 723.903 times 10 raised to 6. FCT now will therefore be, input that on our calculator, that is now 36.45 times 10 raised to 6 times 312.59 all over 723.903 times 10 raised to 6. So I will have here 15, we check first, all right, all right. So that is 15.74 megapascal. But take note, this is your stress at the topmost part. So this is your transform stress for concrete. So divide this again by the value for your modular ratio, which is 8. FC now is equal to 15.74 divided by 8, 1.97 megapascal. 1.97 megapascal. All right. Then the next one for Fs, Fs is equal to, I will have here our moment, which is 36.45 times 10 raised to 6, multiply it by y top, which is equal to 162.61 mm, divide this one by transform moment of inertia 723.903 times 10 raised to 6. Fs now is equal to, input that again on our calculators, that is now equal to 162.61, 8.18, I have here 8.18, 8.19, 8.19 megapascal. Now for short construction, what are we going to consider? Right here, summary. For summary, the stress in concrete will be this one. I have here 1.97 megapascal. And then for the stress of steel, we are going to add now Fs from concrete cure and then Fs from concrete wet. So say for example, let us denote Fs here as Fs1, Fs1, and then Fs1. Fs1 is 27.82 megapascal. So Fs1 plus Fs2. Fs2 and then Fs2. Fs total now will be 27.82 plus 8.19. Fs total now is equal to 27.82 plus 8.19, 36.01 megapascal. So I have here the stress in the extreme fibers for unshored construction. Stress in the extreme fibers for unshored construction. So checking it using the allowable stresses, wherein we have already computed that a while ago. So FC allowable is 9 and then Fs allowable is 148.80 megapascal. So this is way below FC allowable, and then this also does not exceed Fs allowable. which means that this part now, or the stresses, are also adequate under unshored construction. Stresses are adequate under unshored construction, which means that for problem number 1, for this problem, all right, for this problem, the stresses now in the extreme fibers for shored and unshored are adequate, which means it did not exceed the allowable stresses. So this composite diagram now, or composite beam, can be constructed utilizing shored construction or unshored construction. All right, so that is for our discussion under shored and unshored construction. Now, I do hope that you have listened properly because, as I have said in the beginning of our lecture, you will be having now your first seat work for midterms. And it will be placed under the quiz tab now on your Canvas accounts. So I repeat, if you have any questions regarding what we have already discussed, you can always message me at our Canvas accounts or email me at my Outlook or UC-BCF email ad. Now, regarding your plate number one, there are still some of you who did not submit your plate number one. Now, I do not have access on the email which was provided by Engineer Garwageo. Now, if you have submitted now your plate via email to Engineer Garwageo, I would like those students now to screenshot proof now that you have sent your plate via email and then send it to me on our Canvas accounts and then resend your plate. I repeat, these are for those students who are able to submit their plate via email, which was provided by Engineer Garwageo for plate number 1 only. So kindly resubmit with a screenshot now of the email that you have sent to Engineer Garwageo. All right, so that is all for our discussion for today. I hope you have learned again something. And then thank you very much and have a great day.